This lesson is on section 12.3, inscribed angles and intercepted arcs in circles. There's quite a few definitions and theorems that revolve around what an inscribed angle is and what it does in a circle. So we will get started. An inscribed angle sits with its vertex on the circle, and then its sides form chords, which means that the chords hit the circle somewhere else. So an inscribed angle looks a lot like a V inside of a circle. The intercepted arc would be the part of the arc that is on the inside of the inscribed angle. So if you look at this green part here, this is the intercepted arc. It's the part that looks like if it was a Pac-Man, the inscribed angle would be eating the part of the intercepted arc. Okay, so inscribed angle sits like a V inside of a circle, and it eats the intercepted arc. Okay, so some relationships that involve inscribed angles and their intercepted arcs. The main one that you need to focus on is that inscribed angles have a relationship with their intercepted arc. The relationship is the measure of the angle is half of the measure of the arc. So you can see here that this intercepted arc is 68, so its inscribed angle would be exactly half of that. So it would be 34 degrees would be the measure of the inscribed angle. It works, the other way too. If you know what the angle measure is, you just double it, and that gives you what your arc is. There's a side corollary theorem that goes with that, and it says that if your inscribed angle intercepts half of the circle, in other words 180 degrees, it would have to be a right angle. And that's because it would have to be 90 degrees, because half of 180 is 90 degrees. So if it intercepts a semicircle, half the circle, then it's going to have to be a 90-degree angle. That will help us later looking at these kinds of triangles in here. The opposite angles of a quadrilateral in an inscribed in a circle are supplementary. Okay? You get that by simply realizing that each one is an inscribed angle. Okay, so for example, this one cuts from here to here. So it would be half of its intercepted arc. Now its intercepted arc is the 75 plus the 95 put together. So when you add those together, the 75 and the 95, you get 170, and then half of that would be 85. So the measure of this angle would be 85. Now, the angle that sits across from it, its opposite angle, intercepts the exact opposite of the circle. So since it intercepts what's left of the circle, it's going to be half of whatever's left. So you look at that one intercepts, if I can do it in a different color, that one intercepts this much of the circle. So it intercepts the 75 and the 115, which gives us 190. And then when you divide that by 2, you get that this angle is 95. So now together, the two of them take up the entire circle, which is 360 degrees. And so since they're both half of that, they would have to add up to 180. That's why they are supplementary. One little corollary that goes with that one is if two inscribed angles intercept the same arc, they would have to have the same measure. So you can see that this angle on the right intercepts that 100 degrees, so it's 50 degrees. But this angle over here also intercepts 100 degrees, so it's also 50 degrees. So if you see a picture, I always like to think of it looks kind of like a butterfly to me. If you see these butterflies, realize that those angles are going to be exactly the same measure. We can go through a bunch of individual problems, or we can go through one bigger problem that intercepts all, or that takes care of all of these. And so if it will let me switch to my next screen, that would be nice. And we could go through this last problem. Not that it would be required, but it would be good to go through it. Oh, it does not like to switch screens today. Computer buttons, there we go. Oh, look how far we got. Okay. Well, there's your homework. Let's see if we can get up to, there we go. Let's try for this example problem. This has a bunch of pieces in it, but it's all the theorems that we just went through. We're going to go through it one piece by one piece. So let's start with, let's find the measure of angle BDA. So what's the measure of this angle right here? What kind of angle is it? It's a central angle. We learned back in chapter 10 that a central angle is equal to its arc. So since the measure of arc BA is 30, the measure of our angle would have to be 30. Okay. Then let's go on to angle BCA. What kind of angle is angle BCA? Since it forms a V on the circle, it's inscribed, so it would be half of its arc. So it's going to be half of 30. So it's going to be 15 degrees. Okay. We can see that CA, since it goes through the center of the circle, CA is a diameter. So when we talk about finding the measure of arc BC, we're looking at ABC being half of the circle. So that would be 180 degrees. And if we know that from A to B is 30, then from B to C would have to be whatever's left. So from B to C would have to be 150 degrees. CEA then, arc CEA, would be the other half of the circle. So arc CEA would have to be 180. BDC, this angle right here, BDC, we can get that a couple of different ways. It would be half of its arc, so, or excuse me, not half of its arc, it would be equal to its arc because it's a central angle, so it would be 150. Or we can look at it and see that these two angles are supplementary. They form a straight line. So either way, it's going to be 150. Either because it's equal to its central angle or because it's supplementary to the 30. So BDC would be 150. ADC is an angle ADC that goes all the way across. So that would be 180 degrees. Angle DBC, that would be this one right here, this little one. Now this one's going to be a little bit trickier because it doesn't form an actual angle that goes with the circle. It's not a central angle, it's not an inscribed angle, but what you see here is a triangle. And it's especially an isosceles triangle, which a lot of kids don't recognize because CD is a radius and DB is a radius, so they have to be the same measure. And in an isosceles triangle, the base angles have to be equal. So if this one is 15, then this one has to be 15. You could have also gotten that simply from the three angles of a triangle adding up to 180 degrees. Either one would have given you 15. Angle AEC, in order to figure out what angle AEC is, we have to know what arc it cuts. It's an inscribed angle. It starts on the vertex or on the circle, and it cuts the semicircle. It cuts CBA. So since it cuts 180 degrees, AEC has to be 90. CAE, this angle here, in order to get this one, we'd have to know what arc CE is. Well, we can get that because arc CEA we know is 180. So if we take 180 minus 104, that gives us 76. So we know that arc CE is 76, and the relationship between the angle and the arc, it's an inscribed angle, so it's half. So you would take half of 76, and that would give you 38. So angle CAE would be 38 degrees. Angle ACE, same concept. 3 angles add up to 180, or you can take half of it. It's an inscribed angle, so it's half of its arc. So you could take 104 divided by 2, and it would be 52 degrees. The last little tricky one is AEF. AEF is also an inscribed angle, so to speak. Its vertex is still on the circle. It still follows the rules of inscribed angles. So its intercepted arc is also 104. So we would take half of 104, and angle AEF would also be 52 degrees. That's a lot of little stuff, but that's okay. The theorems and stuff are right there for you, and your homework is as follows.